math instructions. And I think jump and MCRs are covered in this chapter, right? Did it say jump and MCR? Or just say math?
Dan says math instructions.
Where does jump and MCR at?
PLC compare jump. Catch what?
Oh, sorry, this is wrong. This is wrong. PowerPoint. That makes sense now.
Chapter 11 is PLC logic and bit shift.
Chapter 10 is math.
Yes.
Okay, PLC math instructions. So what we're going to do, we're not going to play with the total number of math instructions that are available. Here we'll play around with add instructions, subtract instructions, multiply instructions, and divide instructions. We'll also get a look at the other instructions that's available on PLC. When PLCs first came out, they were directly replacing motor controls or electrical controls. So all they would do was just ladder logic. But finally they realized, these guys are computers and computers can do a lot of stuff, right? So they've been slowly adding instructions that we would get in other programming languages besides ladder language, besides the original ladder language. And of course, one thing they added was math, where we can add contents together, we can do this, we can subtract things, we can find the difference. We could keep up with the amount of rejects we have, so we could count coming in and count going out, and then we could subtract them instead of me having to do it. We could let the PLC do it for us, right? So this is basic, right? Input instructions on the left of the ROM. Control devices between L1 and the load, right? Output instructions on the right, one per line, right? Input devices can be connected in series, parallel, or series parallel. Output is only one. Basic circuit. We have what we call a series circuit, and we have what we call a basic series circuit. And of course, a basic series circuit usually consists of a control device, a power source, right? Conductors, a load, and then some device to control the circuit. Or flashlight. Flashlight is about the simplest basic series circuit you have. So normally when we talk about series circuits in PLCs, we're talking about two or more loads, right? That makes sense? So we never have a true series circuit in PLC. Input addresses can be duplicated. Output addresses cannot unless the entire run is duplicated. I think the PLC says you can't use the same output twice, and that is not true. The problem is the PLC, you can use the same output device more than once, or the same output instruction more than once. It's basically called bit instructions. But we had somebody do it last lap. I don't know. Yeah. And what happened is they had two of them working off a switch, but they used the same act. Didn't get an error, compiled over no problem, downloaded it into the PLC, but it didn't work right. It worked like an AND. So this switch and this switch had to become true, because if this switch was true, so if this instruction was false and this was true, right, understand, it took it as what? Being false. So both outputs had to be turned on before the actual true output turned on. So you got to be real careful. This was a trick that we used to use when I first got involved with PLCs. This was way back when they only did ladder logic, and the speed of the speed of the processors were still fairly slow. We were the first The first processor that got put inside, the first processors that we dealt with, the 8088, I'm sorry, the 6800 processor was only clocked at 1 megahertz. That's what we were dealing with when PLCs first came out. Of course, now we're clocking those things in the gigahertz, right? You understand? So the problem we had is that the longer the ladder logic got, an input could change and go away before the PLC scanned the rung. So it would literally miss inputs. Well, what did we do? Well, we repeated the same rung several times down through the logic, but the rung had to be exactly the same. It had to be a duplicate of the previous rung. If you don't make it a duplicate, then you'll end up with some type of logic, right? It won't work the way you think it. And I'm glad that happened, because I didn't put this in, by the way. This is the last time I taught the class. But you can duplicate outputs, but you got to duplicate the whole rung, right? If you set them up, and this one it takes this logic to energize, this one takes this logic to energize, then both rungs have to be true before the output actually comes along. True. Inputs and outputs must be placed horizontally. We don't have to worry about that. Signal flow must be from left to right. We got to worry about that. If we put contacts where we close a contact and it flows backwards, we see this done in motor controls, especially sensors, every once in a while, because the people have to design their own. Diagrams must be numbered, commented correctly. What we're doing is requiring y'all to use what? Well, no, commented.
Commented correctly.
Yeah, we're not using comments though. We're using what? Symbols. Comments mean nothing. What we're going to find out, the PLCs past the 500 series are all requires you to give these guys names, right? You understand that? Because now, if you give it the same name, it'll give you an error. You can't. Y'all notice you can't give the symbol what? You can't give another address symbol the same name. The only way it lets you repeat the symbol if the address is what? Exactly the same. So it takes care of you. You can put a comment wrong all the time. A comment don't care. Comments doesn't mean anything. So you can call two comments. You can say motor contactor 1 and motor contactor 1, and you're not going to get that error, right? Even though you assign them to different addresses. The location of coil contact locations, numerical cross reference. Are y'all okay here? Y'all understand that now? Huh? Programmable controllers is a digital computer used for automation, typically industrial electromechanical processes such as control machinery or factory assembly line and amusement ride or light fixtures. These guys, you're going to run into them in commercial air conditioning systems. You're going to run into them in elevator control. They're primarily the ones that actually run your elevators now. Instead of having all these relays trying to figure out if this button's pressed and this button's pressed, who's got the priority and all that kind of stuff. On the Logic Pro, it comes with you can download a lab book, and one of the things that you attempt to program is a elevator. In the elevator, they give you the simulated elevator and the simulated push button, and you try to program when this button figures out the PLC's got to determine if it needs to run the motor forward or run the motor backwards and all that kind of stuff. Program is a group of instructions organized in such a way to make a computer perform a lot. And this is who you are in this message. You're what? You're a programmer. Now, programs, we talked about machine language. What's machine language? Huh? Machine language is the binary language of the processor. It is ones and zeros. This processor in there, the only thing it understands is ones and zeros. So what we do is the processor is in basically two modes. It's in the fetch cycle. The fetch cycle, whatever binary number comes in, it considers it to be an operational code, an instruction. And then it switches to the execute mode, and what does it do? Well, it does what the instruction did what? Told it to do. And then it switches back to the what? Fetch, execute, fetch, execute. So we got a big list of operational codes, and they're all binary. The first PLCs I saw, we had a 360, an IBM 360 on the front panel, and it had, good gracious, a bunch of just toggle switches on the front. And you could literally enter the program into the computer memory by looking at an opcode chart and flipping those switches to get what operational code you did and push a button. And it was stored in your memory. And then you'd have to figure out what the instruction was supposed to do, which was pretty. Then they came out with a language called assembly language, which was written using mnemonics, basically abbreviations that we could use to represent instructions. But the processor had no idea what a mnemonic was, right? An abbreviation. So what did we have to do? We had to convert it. So the program that converted it over was an assembler. It was really cool. We can actually see an assembly language program. I'll try to show y'all that. So we can't do it anymore. They took this feature away from us. So this is machine language, guys. It uses the ASCII code when it sends information to the screen. It uses the ASCII code, so you can actually see the ASCII code over here. These are constants. Now, of course, what it's doing, what debug is doing, is not displaying the binary codes. It's displaying everything in hexadecimal form. This is what the computer says. It sees nothing but binary. But it has the ability to process information, so we can turn on dots on the screen and display anything it wants to, right? As part of the application. So when we first got into these guys, this is the language we learned, was machine language. The first trainers that we had on microprocessors were machine language trainers. You didn't have to learn the operational codes. But back then, the 6800 had maybe around 127, 128 instructions. So you could put those in a chart, kind of like the ASCII chart, and you could look them up pretty easy. Now they got thousands of instructions, so it'd be really, really hard. You know, these were 8-bit processors, so an instruction had to be 8-bit. So that means the maximum you could possibly have was 256, right? So now we got 64-bit processors. And we not only have these very complicated instructions that manipulate data and do logic, we also got all the instructions that handle the video in the machine. Used to, video was handled by a very, very complex machine language program, but they dropped that down into a single instructions now, which is really, really neat. So then we moved into high-level language. It's like what? BASIC was the first language, which was developed by Microsoft. That's an interesting story too. So we wouldn't have had copyright and all that other kind of stuff if we went from Bill Gates. They had wrote the BASIC and translator, and they was going to show it at a computer show, and by the time they got there, just about everybody in the whole thing already had it. And it made Bill really mad. So it was copyrighted, and now we run into problems. So an instruction. What's an instruction? No. Depending on what level language you write. So what we're doing is we're writing in a language called ladder language, right? And then the processor don't have to do that. So every time you download that thing, what does it do? Compiles it. And when you click that little bar over there, it checks to see if it's going to compile okay. We already know it don't mean the program's right. It just means it's got the right syntax, right? Program, a group of instructions. Okay, we're going to talk about that. An operand. The book uses this term all over the place, but it does not define what an operand is. So what we got these binary numbers that tell the processor what we want to do. We call those opcodes or operational codes. Then we have what the data that the instructions actually operating on, and we call those operands. So the part of the instructions that specifies the data is being operated on and manipulated. So we add two numbers together. What's the two numbers we add together? They're operands, right? And what's the sum? It's an operand, right? So all the data we're going to use in this, everybody know what an integer is, right? Yeah, it's a number without a fraction. Can be assigned a floating point number. You're not going to see a floating point number, the term floating point number is used very often in newer PLCs. They call them real numbers. So if you get into Siemens, that's what they call it. It's a real number, which means what? It can have fractional components, and it also uses scientific notation. What's scientific notation? Huh? Scientific notation is a method of representing very large and very small numbers when you have a fixed number of digits. So my calculator has got so many digits on it. If I exceed the range of that, right, you understand? It's going to take a number times 10 raised to some power. Now the problem is it's still going to keep the number of digits. So what happens is it starts rounding, right? You understand? So the bigger the numbers are, the more it's going to round, because the more digits in the fractional components, you're going to do what? You're going to have to drop. Absolute value. What's the absolute value? Yeah, so it assumes everything's positive. It drops the sign. An array, this is the group of operands stored in a consecutive memory address that we can address them using special instructions that we'll talk about later on without actually specifying the address. It's pretty neat. Scientific notation, a method representing very large and small numbers in terms of a decimal number multiplied by some power of 10. So example would be the number times 10 to square. Engineer notation, we use that here. We don't use it in PLCs. We use scientific notation. But if you entered in engineering notation, it would just be scientific notation. A version of scientific notation which exponents of 10 move in one. It's divided by 3. Constant, we already know about that. Relative to programming a number that cannot be changed without changing the one. Yeah, the instruction. Variable, relative to program a number that can be changed without changing the program. Right? Everybody okay on those? Integers have a range of, a standard integer has a range of plus 32,767, if I get that right, and a minus 32,768. And we know what happens when we use signed numbers, it uses that most significant bit, right, as the sign. If it's a 1, it assumes it to be what? Negative. If it's a 0, it assumes it to be positive. And it uses something called 2's complement, which is really, really cool. So why they call it 2's complement is we'll take a binary number. And y'all don't have to know this. I just wanted to explain it. We'll take a binary number. So we'll come up here and take that binary number right there. So what would that be? 85? Somebody convert that over and make sure I did it right. 5 times 16 is 80 plus 5 is 85. So this would be 85. So what I'm going to do is I'm going to come over here. So the way we originally taught to do the 2's complement is you take what we invert everything. We call that the complement. So I turn this into this. Right? And then I would add 1 to that. So I'd end up with AB, right? Okay. So let's say I add, and this would be considered, since we're using 8 bits, so this would be our sign bit, so we'd say this number would be what? Negative. And this number right here would be what? Positive. So what would happen if I took a positive 85 and added it to a negative 85? 0. Let's see if that works. Of course, you have to know binary addition. So I'd go 1, 0. Okay. 0, yeah, 1. Then I'd go 0, 1, 0. I'm off, guys. I got myself confused. 1, 2, 3, 4, 5, 6, 7. I thought I might have one extra bit over there. So what's 1 plus 1? Okay, so that would be a 0 with a carry of 1. What do you think 1 plus 1 is? 0 with a carry of 1. 1 plus 1. 0 with a carry of 1. 1 plus 1. 0 with a carry of 1. 1 plus 1. 0 with a carry of 1. 1 plus 1. 0 with a carry of 1. 1 plus 1. 0 with a carry of 1. 1 plus 1. 0 and ignore the carry. Yeah, you ignore it. That's why 2 complement works. You ignore the carry. So I added a plus 85, so it's got the most of this bit cleared. I have this one as a negative, so I added a negative 85 to a plus 85, and my answer was what? Is that good? And that's what they came up with 2's complement. So the computer uses 2 complement, but what happens is we still, you don't have to understand that, but that's what it uses. So if you ever use the term 2's complement, this is what they're talking about. It lets us add signed numbers, which is really, really neat. So most processors can't subtract. They just add signed numbers. So I don't think the 1100 supports this, but some of the Allen Bradley PLC, you set the status register 2 or status data set to bit 14. It allows you to do what? 32-bit math. And this extends our range up to a minus 2,147,483,648 to 2,147,483,647. But we still have what? One negative more than we have positive. And why is that? 0 doesn't have a sign. So there's no such thing as a plus 0 or a minus 0, right? Scientific notation. Now how they come up with this, I don't know, guys, but this is huge. So here we have plus or minus 2.4023 times 10 to the 38. And why they don't split this up, I'd have to do some more research on it. So plus or minus 1.17550 times 10 to the minus 38. These are huge numbers. Alright, understand that. Huge numbers. But they're not going to be that accurate because they're going to be rounded a lot, right? I understand that. The book says data file 8, but we know we can use other data files, especially on the 1100 PLC. And what's the other data files we can use? Huh? Yeah. So this says that. So 0, O is for what? 0 is for output. 1 is for what? Input. 2 is for status. 3 is for bit. 4 is for timers. 5 is for counters. 6 is the control register. We're going to play around with that. We're going to play around with N7 this semester. And then F8 is predefined as what? Closable. And then we can do what? Yeah. These are managed by, this is managed by 500, right? These are managed by who? You. So you can't use 9 for floating point number. You can use 9 for what? Energy. What they've done on the Siemens PLCs and also the 5000 is they don't have any fixed data files. It's up to you to do what? Manage your memory. So these are the math instructions supported by not all Allen Bradley PLCs, but some of them. We can look and see. I'll fire up and hook up to the 1100, and we'll look at the math instructions and see what they're available. We're pretty okay, we're okay on add, subtract, multiply, divide, right? We probably don't understand double divide. We'll look at that. Clear, we consider that to be a math instruction, but what does clear do for us? Yeah, we can change a whole word to zero. We had to do this on Siemens doesn't have a clearance. Well, it does, but you got to use a different address in that. So all we did was just store all zeros out there. Everybody okay on square? What's the square? The square root. I don't know what the square root is. Huh? Square would be a number multiplied by itself. No, it's the opposite of the square. It finds the two numbers that are multiplied to get the square, right? Square root, scale. We do a lot of scaling in machine. Scaling will take the input from a temperature sensor or something like that gives us a voltage over a range. So you might get 5 volts might indicate 90 degrees. And we could bring that into an analog input port and we could scale it to mean something. Does that make sense? And it would scale all the inputs for us automatically. We do ramps. Ramp is just basically we used to do this to control DC drives. We call them SCR drives, which required a ramp to actually control them. Also, we use most variable speed AC drives. They call them variable frequency drives, but you got to do more than variable frequency. The speed of an AC motor. Anybody know what the formula for, not the speed, for what we call the field speed? Anybody know what the formula is? And of course, the AC motor will run slightly less than this. Very simple formula. It's equal to 120 times the frequency that we apply to it, divided by the number of magnetic poles. Now, this is the rate that the frequency is rotating around the outside. It's an inducing a voltage into the rotating part. We call it the rotor. You've always got to have a difference between your field speed and your rotor speed. So your rotor is always running slightly slower than the field speed. It's technically referred to as slip. So the minimum number of poles we could have is what? 2. Got to have 2 poles, north and the south, even though they're swapping, right? So how fast would this motor try to run? On Alabama Power. Anybody know the frequency of Alabama Power? Technically, we're not. Let's rephrase that. Anybody know the frequency of the power grid in the United States? Nobody in this class knows the frequency of the power grid in the United States. Not the voltage, the frequency. 60. Yeah, 60 cycles per second. We say hertz. Hertz stands for cycles per second. No. We have all types of voltages. We got all types of voltages. At your house, we basically have 2, right? What we call 240 and 120, but that's. So how fast will this motor try to run? 120 times 60 divided by 2. Now 3,600. So that's the fastest. That's the fastest we can run. And that's if it's 2 poles. This is a 4-pole motor right there. What we use half this, so that'd be 1,800. But if you look at the nameplate, it says I think it says 1,725. So your rotor can never run at the same speed because we got to have a difference in speed between the two. Like I said, they call slip. So technically it looks like, so this is, you got a ceiling fan, anybody got a ceiling fan? So that's what you're doing is to shift speeds, you're switching the number of poles, how they magnet, how they wire the stator. Usually there's 3 speeds, right? You have a high speed, a medium speed, and low speed. You take that thing and look at that switch. It's got 4 wires. One of them's a power wire, and the other 3 is sending different voltages to the windings on the motor. You also got to control the voltage too. It's kind of strange. They call them variable frequency drivers. Well, what you do to electronically control it. So these guys, they'll come with a little push button panel on there that you can program all kind of stuff. And basically, they're not hard to program. You just basically look at the faceplate of the motor and just enter the information off the faceplate or the nameplate on the motor. And then once you do that, you can program how fast you want it to accelerate and decelerate. And once you got it running, it's just got a little push button on the front. You can just press it, increase the speed or decrease the speed. It's really cool. Well, if I wanted to control it with somebody on the outside, we send it around. And depending on the ramp, that's the speed the variable speed drive will control it. So ABS, we know what ABS is, right? What's the absolute value? Positive. Everything's considered to be positive, right? It's the number regardless of the sign, right?
And a lot worse.
And what brake system. Compute, this guy is really neat. So we got add instructions, we got subtract instructions, multiply instructions. What we do with the compute instruction is we just put the formula within the block. And it does whatever you put the formula in there. So a lot of guys do this to take multiplying and then take the answer of that and divide it, right? So they'll just go ahead and do what? Put the whole mathing formula inside the compute box. The 1100 supports that box. Swap, this is for ASCII. Then we get into our trig functions. Arc, that has a sine, cosine, arctangent. And then we got sine, tangent, and cosine. I know what those are, right? Mr. Shook does, huh? So, but just about all calculators deal with sine, cosine. So, sines and cosines are ratios on a right triangle that we can use to solve for one side. If we know the angle, we can solve for a side, and then the arc would give you the angle with that sine. So, and then raised to the power. You know, say this next bottom. Raised to the power.
Where's cotangent at?
Cotangent and arctangent are exactly the same. So it all depends on your calculator what they call it. Some of them call it tangent to the -1. So some calculators actually put a minus up there, and that's not what we call the arc or the angle that has that tangent. Good question. Each store location in the Allen Bradley PLC consists of what? 16 bits. We call it a word. Memory locations can be combined to handle numbers greater than 16 bits. Are we okay? Of course, this is term. 1 bit equals what? Level equals what?
4.
4 consecutive bits. You just can't see 4 consecutive bits starting counting from the watt. So you just can't go in and pick out any 4 bits and call it a watt. A nibble, unless it's a watt. It's a nibble from the least significant bit. A byte, everybody okay with a byte? This is the big difference between the Allen Bradley and the Siemens. Siemens goes in bytes. So you'll see input ports 0. So the maximum input port, number of input ports you can have on supposedly a slot would be 8, 0 through 7. And then it would jump to the next one and the next one. So that's the big difference between Allen Bradley and Siemens PLC. A word is 16 consecutive bits, one storage location, Allen Bradley PLC. A double word, which most PLCs refer to this as the long word. Double word, this was a phrase coined by Microsoft when they set up the registry. How do you handle information in the registry? Is a really neat file that's loaded off your disk that contains all type of information, and you can access that, guys, but stay away from it because if you don't know what you're doing, you can screw things up really, really bad. And sometimes the information you put in about different hardware devices takes so many bits, they give it to you in a double word. But that's what they'll tell you. And then, of course, they'll switch over to hexadecimal when they do that. And then a quad word, double long word, yeah. So, are we okay? So this is basically review. This is the 4 addressing modes. So an addressing mode, we talked about that last class. What's an addressing mode? This is how your instructions address those operands.
Okay.
So the 2 we're going to predominantly use, starting off with, is immediate addressing. What's immediate addressing? So this is the dang numbers inside the instruction. So those counters, when your preset register, you put 1000 in there, that was immediate addressing. Okay? You understand that? The other addressing mode we're going to use is called direct addressing. Direct addressing, what we're going to do is we're going to specify a register, a data register, and the contents of that data register or that data file. I need to get out of that. The book calls them registers, but they're not registers, they're data files. The content of that data file word is going to be your operand. Everybody understand that? So instead of saying, so we do a counter, when we come over here and we say, counter C, C5 colon 0. And what else we have?
Have your preset.
Yeah, we have a preset. And I could come over here and put N7 colon 0. Now notice I didn't put a slash, so this would pull in that whole word, right? You understand that? So we don't have to specify a word because the counter deals with words. So what's going to be put into the preset? Whatever is stored in N70, right? So whatever we store out in that data file, that's what's going to be put in the preset register. Everybody okay? And this is called direct addressing. This PLC also supports indirect addressing. We'll put a little more work into this later on. The specified register or data file, and I need to come back and change this. The only reason I left this in here is why? For the book. These are not registers. Registers are inside the microprocessor. These are not inside the microprocessor. These are where? These are out in the RAM of the machine. Address that contains the address of the variable of the operator. So what we have here is notice so in Allen PLC you specify indirect addresses by putting inside brackets. It says N10.1. So what's going to be at N10.1? The address of the operand. So here we're going 2 different stages to find where the operand's at. So N10.7 is not the operand, it's the address of the operand. And it gives us the ability to be really flexible in how we get these operands, right? We can do all types of stuff, which is pretty good. Index addressing, we'll look at this later on. This is really, really big. The address operand is specified by what we call an index register. This is S24, and this right here is inside the processor, plus an offset. So we use index addressing to go through tables. So we can store all types of operands in a table, and then we can rip through those using index addressing. And we'll show you on that later on. These are all going to be discussed later. But in our lab assignment, we're going to use what? Immediate and direct. Y'all understand those 2 addresses? Immediate, you've been using that all just about all terms so far. So all we used in counters, all we used in timers was immediate address. We actually put the number in there, right? Are we okay? But I did bring the input in. So if I said I0, that would have been direct. So I did show y'all that. But I didn't tell you that was direct address. So, this is some stuff we need to talk about. So inputs and outputs. So that address up there, int.0/0, that would be bit addressing. How do I know it's bit addressing? Because of the slash. The slash. So slash indicates a what? A bit. So what's that address? Input bit 0, right? I understand that. Is everybody okay? It'd be slot 2. It would be the third slot, but it would be slot 2 because we start the slot numbers with 0. Now, if I said it would be the third slot, that's the way it's wrote, but it would still be called slot 2.
Okay.
But it would actually be in slot 3 in the backplane, right? Because the first slot is called slot 0. And of course, in your PLC, slot 0 is occupied by what? Power don't occupy the CPU. The CPU occupies slot 0. Guys, if 0 is used to default as the word address if you admit it. So if you don't put out there, it's going to put what? It's going to use 0 as the word number. That's what we've been using. We've been using that most of the time, right? Everybody okay? Our PLCs, these are fixed PLCs, so the CPU don't have to occupy a slot number. So these guys, we don't have a slot number for the CPU, so we start with 0, right? You put 0. And then from then on, it's assumed, right? Right? Everybody okay? That makes sense. So we don't have to specify slot numbers, unfortunately. I mean, it's good for us. But if we added an input module on the side of this thing, or an output module, or an input-output module, then it would get a what? Starts with an S. L. O. Yeah, it would get a slot number. We'd have to specify another slot besides 0 because why? Yeah. Siemens, I'm not sure. We got some 1500s over there that has a slot. I need to research that a little bit. Normally, the slot number is not built into it. You have to configure it with software when you install it. You have to tell it what slot it's in. Everybody okay? So into 1.14, this would be what? Input, slot 2, word 1, bit 4. Input 1. This is going to input the whole word, but it's going to be word 1, right? We'll use this a lot. You did it in the counter instructions. In fact, when you said C5:0, you actually addressed 3 words. One of them was for the what? Preset, one of them was for the accumulator, and one of them for the status, right? From the input module location in slot 1 is the register in 2A using a move file. So, by the way, when we use these instructions, these are all available on instructions that use nothing but words. So your math instructions are going to work with words, right? That's the smallest unit you can work with. You can't add bits together. You have to add words together. So if you have to add a word, you don't have to specify a word. Everybody okay? So if I want to use a move instruction, I don't have to specify a word. All I have to do is specify a word number, right? That makes sense?
Kind of like how you wrote 85 with them, you specify what it is.
What's that?
You said
This would be input word 1, right? Right? This would be input word 2. Bit, right? sorry, this would be slot, this would be this. Since we left the slot number off over here, what slot is it in? Zero. So if we had it in a slot, we'd have to still put that, we'd have to put 2.1. If you don't put the slot number, it's assumed to be what? Zero. So this is going to empty input, slot 0, word what? 1. This is going to output slot 0, word what? 6. Right? Note that the slot number of a fixed or hybrid PLC is either set by the manufacturer or figured by the end user depending on the PLC model.
How do we know what that slot one does it have to have input slot one have to have a bit or a word on it?
Yes. So we would put.
So that's how you know that that's being word, not like slot. Slot.
Yeah, but if you don't specify the slot number, it's assumed to be what? 0. But we have certain instructions that only deal with words. So your math instruction only deals with a word. So all we have to do is specify a word number if it's what? In slot 0, right? You understand that? If we get it from that, if we get it from memory, then we're okay. Why I put this last statement out there is the Siemens 1300, 314 Siemens we have over there. Is you literally go in and you specify where these internal ports are at. Allen Bradley's we have is predefined as word 0 and word 1, right? Okay, that's word 0 for input, and data file 0 for input and data file 1 for outputs, right? Siemens, you specify where you want to put those internal ports. So, by default, it puts them at 250, 255 or something like that. It's really good. So that's one of the first things we would have to do if we was going to put it on, run the programs on the, if we was going to develop programs for the line over there, is figure out where we wanted those ports at, right? So everybody okay on floating point? F8 is the one we use by default. If you got the 1100 PLC, which is all y'all's zone, you can also use 9 to 255, right? Everybody okay? So everybody okay over here? Any questions? So here they're actually using F1. Word 36. So these are used, we can skip a lot if we have instructions that are specifically designed to work with words. And all our math instructions are specifically designed to work with words. Right? Are you okay? We'll go sleep on. So the add instruction, we have 2 operands. Well, actually we got 3. We got the 2 numbers we're adding together. And then we got the sum of the 2 numbers, right? Everybody okay? Yes or no? So, 2 operands hold source data. We're going to call them source A and source B. So the add instruction itself does not have an address. Because you're going to add 2 numbers together, right? It's the operands that have the address. So what we're going to do is we're going to put a number in where whatever number we're going to add, we're going to put it in one. Source A and source B. Of course, addition, it don't matter if the big number's on the top or the little number's on the bottom, it's going to come up and give you the same answer, which are added together. So these 2, we're going to specify source A and source B. Both sources can be data files, so they can use direct addressing, right? You understand that? Or it can be immediate. Well, you would never add 2 constants together. Immediate addressing. You would just use the number. So I wouldn't use an instruction to put 5 plus 5. I would just use what? 10. Right? You understand? So they're saying one of the numbers can be a constant, but the other one has got to come from somewhere else. Yeah, and N7 or where we're getting it from, we can get it from our F8. You can get it from the input. You can get if you can address your inputs, you could get it from your input port. You'd say N what? Right? N:0, right? And you'd pull that sucker right out of the input data file, and you could add it, and then you could turn around and store it in the output. So the results of your math operation, you could store it in a 16-bit output port. A lot of y'all think what you're doing is storing information directly to the output. You're not. The PLC's taking care of that. But what we're doing is we're storing those ones and zeros in a data file. And then when the PLC reads that, it reads those ones and zeros and decides what to do with them, right? The inputs, it'll bring it in, it uses those directly so it can process them. The data files, outputs, it reads the ones and zeros and it turns the output ports on that's got a 1 in that data file, right? And it turns it off if it's got a watt and 0. But it's a data file, guys. So we can address these two data files directly. So I can take the contents of the input port, right? Input : 0, right? Or that would take word 0, and then I could add it to another number and then come up with an answer. And what could I do with my answer? I could store it in an output port. So we can put anything in those output data files we want to. And that's one of the reasons we can force things, right? Either both sources can be data files or one, so this would be direct addressing. One source can be a data file while the other can be a number, which would be a media address. But both of them, both the source A and source B would never be the numbers themselves. You understand that? You understand why? Yeah, you just might as well go ahead and do math yourself, right? So if my calculator would only add 5 plus 5, what would you do with your calculator? Every time you hit equal, all you got was 25. What would you do with that calculator? Wouldn't be worth anything, right? So, or your cell phone would only dial one number. The third address would be where we're going to stick the what at? Thumb, and that's what it's called, a thumb. This is where, and this is going to be direct address. You can't use immediate addressing to store the sum. We got to put that in a data file somewhere, right? Everybody okay? Any questions? Yes, no? No? So this would be an example of an add instruction. So it's a block instruction. It's on the right-hand side, so it's considered to be an output instruction, right? Can't put two add instructions in series, right? Understand that. We can put them in parallel, but we can't put them in series, right? So this is direct addressing. So it's going to take whatever stored at N7 word 0, which currently now is what? 0. It's going to add it to what's ever in source B, which would be word 1, right? You understand? Where's it going to put the answer? It's going to put the answer in word 2. Now you got to remember, we're going to be limited to the signed numbers, right? 32,767 and 32,768. Can't put more than that in a single byte, right? I mean, a single word. Everybody okay? We got to deal with numbers of that. We'll probably figure out how to do long words. If the PLC supports that, we'll see if 1100 supports the long words. Yeah, that's just what would, well, when you're writing the program, it has no idea what's out there in N7:0 while you're writing, right? Understand? Because we're not online with PLC on the right program. So by default, it's going to put that 0 in there. As soon as you go online, download and go online, it should put the numbers that are coming from that file. That's a good question too. So right now while we're writing it, so as soon as I make input 1, input 0 slash 0, as soon as I make it true, it's going to add these two numbers together and it's going to store it right. We're okay? Any more questions? 16-bit numbers, right? Or words. But we do have problems. We can overflow our things. So it deals with signed numbers. So if you add two numbers together and you exceed the range, I mean, it's still going to give you 65,000. So I can enter 65,536. But if I add it to another number that's that great, it's going to overflow the sign. It's going to change the sign of your answer, right? Understand that? So if I have a positive number where I add two numbers together and it comes up to be greater than 32,767, it's going to switch to negative. But what's it going to do? It's going to give you an indication. So we have inside the status file, we have a carry, which means we carry out of that, right? Overflow means we change the sign. This flag indicates the results of the math operation for 0, which is what we just did. So if I was to add a positive 5 and a negative 5, then it would come up and give me 0. So what it would tell me is if I looked at that flag bit right there, if it came up to be 0, it would tell me that the two numbers were exact opposite, right? It would be one of them with the same positive and negative numbers would be the same. And then we got the sign bit that we can examine this guy right here. It said S203. If it's set, it tells us the number in that will be what? Negative. So y'all understand the flag bit? Well, this is that S2 register that we have access to, right? Understand? This is the register. This is actually inside the processor. So you're actually addressing the status register of the processor. Yeah, that's what it said. The overflow flag will be set. Are we okay?
So are we going to be inputting those entries?
Are we going to be doing what?
Inputting these addresses? S2:0.
No, those are, this is used by default.
Okay.
So what you would do, when you bring it up, and I don't know if RS Logic set up. Let's go ahead and take a break, guys. 10 minutes. Let me go back into RS Logic to show you the math instructions that we have available. I got it running. So here's math, right? Okay. So the 1100 can do what? Can y'all see this? Let me blow it up. No, it don't blow that up. Add, subtract, multiply, divide. You can do square roots, right? Negate. What negate does is it changes the sign of a number. So if you got a positive number, you want to make positive. If you got a positive number, you want negative, then you can use the negate instruction. If you got a negative number, you want to make positive, you can use this instruction. This instruction right here we'll use later on, TOD. What this does is it takes BCD information and converts it over to binary. Because all your numbers, by the way, that you're doing addition with, those are binary numbers, right? Even though your application is displaying them in decimal, thank goodness, right? The actual math is in binary. So if I was to send information from thermal switches or something into the PLC, it would be considered to be binary. And that's not the same, guys. So what we'd have to do is convert them back over. And then if I wanted to send it out to a display, most of your displays are BCD. So you need an instruction where you can convert binary over to BCD. So it's those two instructions. So here's our move instruction. So what do we put there? We could put a number, not that big. And then we have a what? Destination. Where do we want to put that? We could put it in any data file you want. You could stick it in a bit file. You could stick it in a timer file. You could stick it in. Now remember, your timers, you would have to specify which file because we call them timers, but each timer actually takes up 3 words a minute. One of them holds your preset, one of them holds your accumulator, and the other would be the status register. And this is also true. So if I wanted to change the accumulator, if I tried to use an address, then I would have to know what address it was. But what they give us is they give us the ability to address those things by name, right? You understand? So we could use ACC. What would that be? Accumulator. I think PRE is what? Preset. Oh, so this is where you want to put it at. Destination cannot be immediate address. The destination has got to be one of these other addressing modes. The addressing mode that we talked about would be like M7. We could put F8. We could put, we could store it in an output. We could store just about it. We could store it in the time. I could come over and I could say P4:0, right? You understand that? Dot ACC. And it would take that 1000 and do what? Put it in the accumulator of timer 0. So any data file, guys, you can address with the destination. So the source can either be the address. It could be the address of where the operand's located at, and that's the other three addressing modes, or it could be the operand itself, which would be immediate addressing, right? That makes sense. Huh?
So do you have to have a timer?
No, I could put it anywhere. I could come over here and I could say output : 0, 0, right? Dot 0. Because it's a whole word, right? Okay. Right? Don't understand? I could come up here and I can say destination might be, what do you want? R6 : 0. Right? Understand? So anything over here inside these data files, you can address them. But it's going to be a whole word. You got to deal with it. So I didn't have to put that period while ago. I had to put it on the accumulator for the timer, because I didn't want to specify the address. I wanted to specify it by name, right? You understand that? But these other ones, we don't have to specify which slot it's in. If it slots it, we have to specify what the word number, right? Everybody okay? So this can be direct addressing. So I could come up here and I could take the contents of N7 : 0. And then I could put it where? This would put it into R6, which is a second control. It's a control register we can use. We'll use this register for shift instructions, rotate instructions. We'll talk about it later on. So shift instructions are going to take a whole word and move it one bit, either to the left or to the right. So we can do sweet things with that. So if you move it to the left, you're going to multiply it by 2. Every time you shift it, you multiply the number by 2. But we got to do something with that bit that goes out. We'll talk about that. So any of these are available, and also on this PLC, we have what? We got I could use R55, right? : 0. 0, Rich. What I think I put a semicolon. Yeah, I did. Okay, that makes sense. So your destination cannot be immediate addressing. And I'll show y'all later on. If you look at the actual instruction inside the instruction set for the 1100, it tells you the addressing mode that's available for this instruction. So if you don't, so what's the addressing mode? That's a good test. Is how we tell how we're going to address that operand. So we got immediate addressing. What's immediate addressing? It's the number. The number is part of the instruction. It would be a constant, right? You understand? What's direct addressing? Yeah, that's when a data file holds the number. So I specify the data file. And then as we move along, we'll explain the indirect address and then the indexed address. We'll play around with both of those. We got to have something there. By default, you know, when you download a program into those things, all your data files are set to what? 0, unless the inputs and outputs will take the first scan that will come through there. So what we have to do is we have to come in and we have to establish numbers. So in here we might. So this is Logic Pro. So the addresses still work out. We'll input 0/0. Notice the bit number doesn't drop to the bottom, so that's one little different like it does on. But I could come over here and I could say, you know, I'm going to move a number. Okay, we can move 10, right? And where do we want to put it at? It converted it to hex too, so it didn't keep it in decimal. So we can come up and do, then we can put it somewhere. So let's put, no, we're going to do math. So let's put it in one of our integer files. Right? Make sense? Okay. Then I could come up here, since this is an output instruction, what you can do on your program, and what Tyler was bringing up is the way we're going to do the lab. So what we're going to do the lab is we're going to do it very similar to the way we did the logic, where we use the same ones, right, the same switches to do our what, our AND, our OR, our NAND, our NOR, our NOT, right? Understand that. Well, here we're going to use the same two numbers, and we're going to do what with them? We're going to add them, we're going to subtract them, we're going to multiply them, and we're going to divide them. So what we can do is, and by the way, this doesn't have the palette. That's one thing I don't like about this. And another thing that gets me screwed up is you scroll through the tabs here on Logic Pro, and on 500 they're up here on the side. So you'll see me go up here all the time looking for them. So we'll go back to our bit instructions, and then we can come up here. I'm sorry, user, and we can put a down drive, right? Oh, let me highlight this. All right, did it. Then I'm going to take this move instruction and put it here. And then I can come over here and take another move instruction and put it here. I do that all the time too. I try to pull the tab down there. Anybody ever do that? I do that all the time. As long as I've been dealing with this. And then we can take another number and do we can make it like 53 or 54. It don't make any difference. And, it looks like Logic Pro is actually converting it to hex. So 500 doesn't do that. And then we can put it in another word. So we can put it in N7-1, right? Then I could come down here and we could use a switch, or we could do it automatically. Output instructions, some output instructions don't necessarily have to have a control device. You got to have an output instruction on every rung. Everybody understand that? Every rung. Do you have to have an input instruction on every rung? No. If you want an instruction to be executed immediately every time it's scanned, you just don't put an output, right? It'd be an unconditional rung. So let's do it that way first. So I'm going to go to the math instructions and see what this guy supports. So what do we want to do? Yeah, we'll add. Another thing that I like about Siemens is that once you enter a rung, it automatically sticks a blank rung. It automatically sticks a blank rung. It always keeps one blank rung below you. So you don't have to constantly go back and do what? Insert this rung. I really like that. Of course, Siemens don't call them rungs. They call them networks, but it's the same thing. So we're going to have to go all the way back to user, and we'll insert a line, right? And then we'll do it without input. It just won't cause an error. It works fine. Go back to our math instruction, and we'll use the add instruction. soon as it pops on the right, we know it's an output instruction, right? Well, I didn't put anything up there. Oh, sorry. That's a good point. I don't know where they came from. So this is source. We'll come up here and we'll take this N7. So one of the, when you add, one of them can use immediate addressing, right? Both of them could be direct addressing. One of them could be immediate addressing, but they both can't be immediate addressing. Everybody understand that? One of them has got to use another addressing mode except immediate. Otherwise it's points, right? Always adding 5 plus 5. So here we're going to use direct addressing in both situations. So I'm going to take 0. And then I'm going to come up here in my source. Let's do it. I'm going to take N7:1. And then we got to pull it somewhere. Your destination cannot use immediate addressing. Right? So,
Preset of the counter.
You could put it in a preset of the counter. You could put it in an accumulator of a counter. You could put it in the preset of a timer. You can't change the multiplier. You could put it in the accumulator of a timer. So if you wanted a timer for some reason, especially down counters, you could literally make it down. You can make it count down, guys, but you have to preload that accumulator with a number. And then it would actually count backwards, but the problem is when you reset it, it would go to 0. So you would have to do what? You'd have to load it with a number. I'll show you that too. So we'll just put this in the next address. We'll just put it in 2. And then there's our program. Now, another problem we have with Logic Pro, it don't show errors. So that means I could come over here and do something crazy. I could come up here and grab a coil, and I could come up here and I could put it in this instruction right here. This is another thing I don't like about it. And I can assign it an address. I could upload this, but the run won't work, but it would still download to the PLC. So that's another thing I don't like about this. But this is a really good simulator. I do know some of my students that's actually teaching PLCs using this right here because they can't afford the PLC. This guy right here, for a permanent license is like $45. So we're going to download this. So we come over here and we'll download it to the PLC. And then we'll go online. And then we'll switch to run. So I'll come up here and, oops, wrong thing. Let's take it out of it. What I'm going to do over here is, I don't need to take my project tree, is I'm going to come up here and bring up my IO simulator. And it pops up over here on the side. You can see it's got a nice array of simulations. It's got 2 input, 16-bit ports. This is simulating a modular PLC. Which I think it's got 16-bit input port in slot 1. It's got a 16-bit output port in slot 2. It's got a 16-bit input port in slot 3. And it's got a 16-bit output port in slot 4. It's got some BCD switches. We can come up here and click on this, and it sends BCD back to the thing. But it's BCD, it's not binary, right? You understand that? So it's a code. So we need to have some way, if I wanted to do math with this, I need to convert this over to what? Binary. So we've got instructions that do this. And this is a BCD output right here. So if I'm going to make this thing display a thing, I don't know, I think this might be hex. Oh, I think it'd be hex too. I'll have to go back. You can change the type of input you have just by right clicking. So I got what available. I got a push button. I got a normally closed push button. I got a normally open limit switch. I got a normally closed limit switch, and then I got a regular switch. So it's up to us. So we'll change it to a push button. So I'm going to close this up so I can see more. And this is the only one that we'll deal with. So let's switch it to run. And what we'll see is I'll come up here and push this button. And nothing happened. Let's download from here. Download from here. And switch it to run. Oh, I know what I'm doing. Duh. Let's go duh together. Let me go duh. Duh. You know what I'm doing? Yeah, thank you. I use an input address that we would use, so I'm getting confused between the two PLCs. What input address should I have used? Yeah, I was just seeing if y'all were paying attention. So let's use input colon 1/0, right? I'll re-download it and then we'll switch to run. And I'm wrong PLC, Rich. Press 0. And what did it do? It added what? It didn't add this. It added the contents of this, right? And contents of this register to the contents of that register. And then it put it where? Yeah.
Then you can take like 872 and add it with something else.
Yeah, so you can take the sum of the sums and add them together, right? You understand that? So what we're going to do in the lab is that we're going to develop a program very similar to what we did with the logic instruction, where we're going to use the same numbers doing this. We're going to use the same numbers because now what I can do is I can come up here and play around with this and change the numbers without having to go to each instruction and change the numbers. And then we should know right off the bat what our results are going to be. The only thing, guys, is when you deal with the divide instruction, what can you end up with? A fraction. You know? So your divide instruction, you're going to have to use one of your F8 data files. Your add instruction. So what I would do in that lab is what would I do next? I would come down here and I would insert another rung, you know, and then I would do a what? I would put a what? Like a subtract instruction, right? And then I would take the same two numbers and do what? Subtract them, multiply them, divide them. Don't store them in the same data file. Don't store them in the same data file because every instruction will wipe out the other one. I don't know if I want you to put odds are, I don't know if I want you to put a control. So here it would only add them when I did what? Press that button. This would move them into a data file and they would be sitting there. Right now it's doing it immediately, right? So anytime I change these numbers. But this is what I was talking about. The beauty of this is I could come over here and what we'll do is we'll come over here and change these switches. Because they're just a lot harder. Sure, I can store anything I want to. Here we're just trying to see how these work. So yeah, the F8 data file could be from a math operation itself. It can be from a divide operation. It can be from a shift operation. It could be just about anything you do to manipulate that data. So we can manipulate the data in these data files just about any way, right? Understand? Does that answer your question? So what I'm fixing to do is I'm going to change all these switches to this. And I can address this port, right? The whole word. I can address this whole word. That's why I like to use these. None of our PLCs that we have available gives you a word that you can deal with. So it would all depend on them. So here we got this port. So what I'm going to do here is I'm going to come over here and let's take the source up here and change it to input 1/.0, right? I don't think we might not. We don't have to put that. Let's see if yeah. Because it's understood to be the word, right? You understand that? Because this instruction here only works with words. And so what do we need to do now? Need to download it and then switch to run. So I can come over here and I can close this, whatever I want to. And then when I come over here and hit that switch, what did it do? Well, no, it did. It's showing me the binary equivalent. This is not decimal over here. And that's what you got to understand. These numbers coming into the PLC are considered to be binary. Right? You understand? So if I come over here and, but what your RS Logic 500 application is doing is converting it to, it's displaying in decimal form for us, which is nice, right? I should, let's go, that's no problem. So I'm going to change this guy here over to 3 because I'm using it as part of my number. So let's go over to 3, right? Colon 0. Now we can use this whole port right here, and what I'll do is I'll change this to a push button. Then we'll download it, and we'll put that. And of course, when I press this button, oh, dang, I did it again. You gotta take care of me tonight. Can you see what I did? I didn't give it a bit. I thought I did give it a bit number. I used a dot. Okay. We can't do that. So what would we do here? Got it on run. Oh. Yeah, I need to turn all these guys off.
And then it won't change until you press it.
That won't change because the move instruction is not executed till we do what? Yeah, so as soon as we press the push button, here it comes over and sees 4, right? Which is okay. Let's go ahead and close this one and close this one. So this is 15, right? But it's R and F. And when I come over and press it, it's gonna display 15 for us. So what it's doing, it's displaying these binary numbers in what? Yeah. So if I was to come over here and use this input right here, and I put a 555, I wouldn't get 55 into this instruction because 55 BCD is not 55 binary, right? Y'all understand that? So, no, we wouldn't do that. We okay? So now what I can do, as long as I don't have a number greater than 32,767, then what can I do?
Put it in.
Yeah. So I can, so 600, so now we're dealing with true variables, right? You understand? I could take this output, and here we're putting in, let's say we take the sum, and what I'm going to do with the sum is I'm going to come over here on our add. This is our destination, right? And I'm going to change this to output 2. Output colon 2. So we'll download this, and then we'll switch to run. And then what it's now is sending this number to that output for us. But this is what? This is binary, right? Yeah. So any of these files on the left that are addressable, I'm trying to make them all the same color. So you can change the color of them by right clicking on it, and you got red, green, or yellow. That makes sense? Which is pretty good. So now I could come in and I could just set in any number. And what we're going to have now is when I press this button right here, the output port actually does what?
So that's 301 binary.
Yes.
If you were to write that down.
Yeah. So if you took this right here, which is the answer, right? Which is what?
301.
Yeah.
301.
If you took that right there and you went through that whole process of converting that to binary, it would come up and give you this number right here. So what we find out is we need to understand binary, right? Now what we're going to find out, guys, is we have instructions since we deal with BCD, so we're decimal people, right? You understand that? That's the numbering system we understand. No matter what country you're from, that's everybody understands the decimal numbering system. We don't understand. Computers love binary. The only number system that computer right there basically understands is what? Binary. But we have instructions where we can make that computer can do what for us? It can convert it for us. It can do the math and convert it for us because it can process information. So we got two instructions. We got the TOD and FDR that can take something that gives me a BCD input. So I can input the number 153, and then it'll convert it from decimal BCD over to what? Binary. We can do math with it, right? And then when I want to display it, I can send it back out I can convert binary to BCD. So we got two instructions. Every PLC that I've ever worked with has that ability. Because why? We need to be able to input numbers, and we need to be able to see numbers. You know, I was looking at the speed of a motor, and it said AB39. What would that mean to me? Right? Go ahead.
The red is a 1, the black is a 0.
No, yeah, the yellow is the 1.
Yeah, this one.
Oh yeah, you mean over here yeah, I see that. All this.
60 high.
What's that?
When I do the conversion, it's 1 0 1 1 0.
So this is the most significant bit down here.
Okay. Sorry to hold it the wrong way.
Yeah, this is the most significant because this is bit 8, right? Yeah, this is 1, 2, 4, 8, 16, 32, 64, 128, 256. So we know it's got to be greater than 256, right?
I started from the top and go down, so I can start from the bottom.
Yeah. So here's your most significant bit down here. Notice this is bit 8, and that up there is bit 0. Now we couldn't do it real fast, but you know, I came down here and get this. This was the 256 bit, right? Well, I know it had to be greater than that because why? Because we had other bits set down. I know it had to be odd. Why did I know it had to be odd? Because this bit right. So I knew I was expecting a number greater than 256, and it had to be. So 301 makes it. Worked, didn't it?
Yeah, it worked the other way.
So what we would do next is just do what? We'd take the same two numbers and we'd do what? We'll subtract them, then we'll take the same two numbers and we'll multiply them. We'll take the same two numbers and we'll divide them. So you're going to draw your logic. You're going to put one run to do each math operation. You're going to put a master start stop on the thing. So all your diagrams have to have a what? Master stop, stop, right? Did I say that right? Did you say Well, I'm going to come back there, and that's why we're using these registers. I'm going to come back there, and I'm going to put numbers in there, right? And I'm going to put any number I want to. And every instruction should be able to handle the math. Now, which means if I put a number where the sum comes up to be greater than 32,767, then it should switch to what? Negative, yeah. And if I take two numbers that divide and I get a fraction, then you should be able to handle that. So you're thinking, well, why don't I put two numbers that'll never give me a what? Fraction. So that's a good point. I'm glad you brought that up. So what's our master start stop? We'll come up here and we'll put a start, and then we'll do a what? Put a down drop, right? We'll put it the way they do it in Germany, and they can never. So over in Germany they put the stop over here, and we're going to do. It's going to be true if it's closed, right? So what I'm going to do is over here is I'll make my stop button a what? Normally closed, so it's already true, right? And then what we'll do is we'll put a down, we'll put a seal in, and then over here, we'll use one of our internal bit files. So this, I'll call it input. So Logic Pro doesn't deal with symbols. So it's not going to pop up and ask me for a symbol. So that's why we're not doing this. So input, this is going to be my start. So it's going to be input 3/0. This guy right here is going to be input 3/1, 1. This is going to be one of our B3 files that we use for internal relay. What? And then over here, we would use just the same address. If you're using symbols, you can just type in the same symbol that you use. Okay. I had to delete this wrong down. So this is the way ours would work. Now, how would we disable everything? Yeah, what we do is we'd come down here in all our rungs and put a what? Yeah, and that's nice by using symbols because you can just not remember your address. No, because it would still do the math.
I got a question. On my reset that we did last lab, I put one switch and then I had a bunch of lines off of it.
That's fine.
About 5 lines. It called it an error.
Yeah, I think yours said it had it exceeded the limits of something, right? I've never seen that error before.
So I just
What
put
you
each
did is
re-
you were resetting timers. You know your problem, right? There's only one timer that don't reset automatically. So the timers reset your time on, your on delay timer and your off delay timer. They reset themselves when you do what? Not when you lose power, when you disable.
Yeah.
So you was resetting something that didn't need a what? A reset. So we have to reset our counter, right? You understand? We have to reset retentive timers. Well, you was resetting all 3 of your counters, and you were resetting timers that wasn't supposed to be reset. That makes sense?
But I still put the reset in after I put each reset on each line, and it said it was fine.
I don't know. That's like I said. Yeah, I remember that. I remember you showed me that. And I think we discussed it then too. What did I tell you then?
I don't think we discussed it.
Yeah, you did. You called me back there. I had to sign it off.
You discussed it with me.
Oh, you had all the resets on it?
Yeah.
Okay, I'm sorry. So your retentive timer and your retentive timer is the only one that needs to be reset.
Okay.
So undoubtedly it didn't like something, and what it didn't like, I can tell you. If it gave you an error code, a lot of times when you get an error, you can go into the status register and look at your error code, but the problem is it's going to be an error code, but then you can go on the internet and say what this means, and it might give you some more information. Are we okay? So y'all can put that, Rich don't know everything. So what's your answer to your question? I don't know. You just did something it didn't want.
It didn't
It
work.
didn't like. So every once in a while, you on your calculator, it'll pop up error. What did I do? You did something the calculator didn't want. Didn't like it. So here we're using the examine if closed, right? You understand that? And that's why we got to use it, because your stop button is supposed to be a what? Normally closed, right? So I come over and press this, and then of course now we do the math. If I come over here and hit my stop button, then everything's disabled, right? We can't change the number. Okay? So this is what we're trying to get used to is using that And it don't have, this is not E-stop, guys. This is not E-stop. Y'all understand that? E-stop has, this is called a standard stop-start station. Or some people call them fill-in, some people call them memory. Some people call it a 3-wire control. Now, how they got that name, I have no idea.
Hey, do the imagery. You start from the.
What's that?
Can you hit the first one? Start.
Yeah, this one, well, we might call star. It actually could be anything. You might need, normally, they call, most people don't call them star. If it controls the motor, they call it run and stop. If you look at the labels on this button, that's what they got in the label. Which is the,
We do the same thing if the stop is on the first, right? So either way.
either way. Yeah. All the way, this guy's got to be in series with the run. And it could be on the right-hand side of your fill-in, or it could be on the left-hand side. Each input instruction takes so long to scan, and it don't make any difference which side you put it on. What I was showing you, if you got into one that was written in Germany, they're going to put the stop on the wall, right of the fill-in. If you get over here, 90% of the time, they're going to put the start on the wall. Unless they learn from German people. So I just want to show you. Yeah, that stop button could be anywhere. Right? It's just a nod instruction. Any more? So what do you want me to do? Now nothing's going to change. It's just what it does is allow these rungs to become true. Right? You understand? This rung right here would still, I don't need to use that because I got myself in a common mistake. I stuck this in there so we can make this condition. You notice what I did?
Mm-hmm.
Yeah, I made my start button. And this is the type of error. This is the type of error that when you check it, it won't give you an error because it's perfectly liquid. Right? You understand that? So we got it in the right syntax, the correct way of writing, right? You understand? But it won't, when it compiles over, it won't work. Everybody okay? This is what it somewhat, but I have to hit the start button and go both of them. Yeah, we probably move this over to another guy. Because we wouldn't duplicate, we wouldn't let, see? So basically, guys, this is just about y'all's program, right? So that y'all understand those instructions now about the add, subtract, multiply. So y'all shouldn't have any problems with it.
No.
Never do. So all you're going to do is, but I'm going to have the ability to do what? Change these numbers. And that's what's nice about using the move. I mean, you could use immediate addressing on all of them, but if I wanted them to see something different, I would have to go back and do what? Change all these instructions. Here I can just come in and change these two numbers. And then next time we load it, or tell it to add it, then it'll do something different. Are we okay? Only for your the quotient on your divide instruction. Because I cannot use fractional numbers in a move instruction. Move instruction is integers. So the only thing that we can run into floating point numbers is multiplication. Very easy, right? Understand that? Multiplication. You can very easily end up with numbers greater than a positive 32,767.
Say source A and source B for all things. We get it back.
No, you'll have to store it as an FA. It's your answer. Your answer is the one. Your answer.
Oh, so the destination.
So I could take 5, which is an integer. I could divide it by 3, which is an integer, and I would come up with an answer that has a what?
Store it in FA.
Yeah. So we have to store it in FA. If you don't do it, it's going to give you the wrong answer because it's going to truncate and it don't even round. It just basically what this sucker does is just drops everything to the right of the decimal point, which means you're definitely going to end up with the wrong answer, right? You understand that? I've never seen it used without a floating point. And like I said, most of the time when we multiply, they'll use a floating point decimation. Because you can very easily multiply numbers and end up with numbers greater than 32,767 without even thinking about it, right? Y'all understand that? So yeah, but we're not going to do that. We're not going to enter any numbers bigger than that. All we need to do is we could, that's what we're going to see, and let y'all actually see a floating point number when we look at the actual answer. What's actually nice down here is that at the bottom of your add instruction, what does it give you? It gives you the answer, right? And of course, if we wanted to see the answer, then we could go to where? We could go to, we could go to output 2 or whatever we wanted to, and here the answer would be in binary form. Okay. But if I stored it in an N7 register, I could go down here to an N7 register, and I could actually see the numbers, right? That wasn't N7 register. Yeah. Now this gives it to us in decimal. I don't know.
Can you change our difference to read it?
Yeah, we got access to that. Yeah. I don't know why you're going to do that, but we could, right?
I thought it was
Oh, I understand. Yeah. So right down at the bottom, I understand what you're showing right now. So I could come up here and display it in binary. I could come up here and display it in hex. I could come up here and display it in octal, whichever number system you're comfortable with. So that's a good point. Thank you. And this is the same thing true on the RxLogic 500. When you display these registers, I think even over here on the output register, we can display it in what? So here the default is what? Binary, but we could do it in, we could do it in hex if we wanted to, right? Let's see that. So 12D is equal to what? 301. So it's whatever you prefer. If it was an output port, then I would probably want to either be in hex or either in binary, right? So I know which outputs to expect on, and I wouldn't have to convert it over, right? You understand that? So binary, it would come up and it would tell me exactly which output should be on and which output should be off. This is why by default it goes to binary. Let's see what we're talking about. Everybody okay? Under the base. The Radex, that's another name for the base. We call it the base, but it's the same thing. Technically, that we call it the decimal point. Technically, it's called the Radex point. Are we okay? Y'all ready to go that?